Okay, so welcome for the second lecture online of functional analysis. So just to clarify some things I was saying from last class, so the difference between Hilbert spaces and Banach spaces is the lack of a projection onto closed convex sets. So this is an exercise that is in, I'll send you with this lecture. So, but okay, what do I mean by this? So in Hilbert spaces, we have the following theorem. If H is a Hilbert space and K is a closed convex set, then for any P, for any point P in your Hilbert space, there exists a unique Kp in K, the projection of P onto K defined by P minus Kp is less or equal than P minus K for every K in the capital K. Okay, so morally what we have is, let's say that we have a convex set here and we have a point P here. Then we can actually find which one is the closest point to P. Okay, this guy here is Kp. Okay, and geometrically this is given by saying that K lies on the other side of this hyperplane. Okay, which the hyperplane is defined by the vector P minus Kp. Okay, but this is not true for Banach spaces. Okay, so let's see what do I mean by this. So not true for Banach spaces. So let's take an example to show this. Let's take C0 of, let's say 0, 1, C0 of 0, 1 with the infinity norm. And we take K to be the convex set which is given by f in C0 such that the integral from 0 to 1/2 of f minus the integral from 1/2 to 1 of f is equal to 1. Okay, so what is the claim? Or what you would like to do is find the projection of 0 onto K. So one of the things we should check right away is that this is closed. Okay, so if you have uniform topology in continuous functions and you have this functional, so this is a functional that takes a function in C0 and gives you back a number. So this guy is a closed convex set of C0 of 0, 1. Okay, so K is closed and convex. Okay, you can check that, but fairly easy to see. So, but what is sort of the point here? Find the projection of 0 onto K. The point is there exists there is no projection. So there is no projection because we're going to try to find the infimum of, let's say, f minus 0, such that f is in k, and this is the infinity norm. Okay, now we have two numbers. Okay, so we are going to show that this is bigger or equal than 1, and we're actually going to show this is equal to 1. So if we take the integral from 0 to 1/2 f, and let's put a plus just to make things a little weird, plus minus the integral from 1/2 to 1 of f, this is equal to 1. Okay, so we have two numbers that are equal to 1. Then either integral from 0 to 1/2 of f is bigger or equal than 1/2, or the integral from the minus integral from 1/2 to 1 of f is also bigger than 1/2. So we either have this or we have that. Okay, so let's think that we have the first case. So we are going to suppose that the integral from 0 to 1/2 of f is bigger or equal than 1/2. But then this implies, and this is Chebyshev's inequality, or basically just by doing a contradiction, that the size of the set f bigger or equal than 1 has to be positive. Okay? If f is always less than 1, this integral can never be bigger than 1/2. Okay? Which implies the infinity norm of f is bigger or equal than 1. Okay, so similarly, if integral to 1/2 to 1 of f is less or equal than minus 1/2. Okay, and now the point is which one is the infimum here. So the infimum of this guy, so we have to have this condition, the integral from 0 to 1/2 of f is equal to 1, plus minus of this has to be equal to 1. So the optimal f is given by so if here we have 1/2, here we have 1. The optimal f is given by this, and here minus 1, like this, okay, until 1 here. So the problem with this optimal f, the optimal f, let's call it f tar is not continuous and does not belong to K, and hence it does not belong. To K. So I mean, and that's actually the way of showing that this infimum. So we just showed that the infimum of f minus 0 with f in K is bigger or equal than 1. To show that the infimum is equal to 1, we would just take something along these lines. We would take a sequence of functions, which would be 1 plus epsilon, and here 1 minus epsilon. That would do something like this. Around 1/2, you would have a continuous thing, and then it will go like this. Okay? So if you do it in a right way, you can do it in such a way that this guy has the necessary restriction, and when you take a limit, you converge to the infimum, But this function, this sequence of function, this sequence is not compact in C0, 0, 1. Okay, so this is the sequence converging to the infinite. Okay, so it seems that, I mean, having the inner product is not giving us that much of a difference in the structure, but it actually allows you to create a projection, and the projection is what it allows us to get a basis, an orthonormal basis. So without this projection, we can actually not build a basis for Banach spaces. So for Banach spaces, we have to deal with the fact that we can take this infimum, which will be positive, but we cannot actually find a minimizer. Okay, so usually the proof that you have to do in Hilbert spaces with the optimizer, you have to do in Banach spaces with almost optimizers, and then try to make things work. All right, so that's what I wanted to say from the last class. Now, let's change a bit gears and go on to the next topic, which is linear transformations. Okay, so we are going to consider x, y normed vector spaces, and at some point we'll start thinking even vector spaces that are norm, and we are going to take a transformation T, x to y, such that T is linear. Okay, so what do we mean by linear? T of alpha x1 plus beta x2 is going to be equal to alpha t of x1 plus beta t of x2 for every alpha comma beta in R and x1 comma x2 in X. Okay, so this guy is also in Y because Y is a vector space and T is just pointing one thing to another. Okay, so the point is that linearity makes some things easier, and it actually makes these guys analyzable. I mean, when you start thinking of nonlinear things, you have to be you have to be really careful about continuity and boundedness and these kind of things. So let's look at the following lemma. Actually, before going to the following lemma, so in general, I mean, for general t going from x, y, we are not going to study much of that. We are going to usually choose y to be equal to x itself, or y to be equal to r. Okay, so these are the set of linear transformations that are going from the same space of the same space, or the linear transformations going from x to r, which are called linear functionals, and those have a structure on themselves that is related to the structure in x. Okay, so knowing something about the linear functionals going from x to r will tell us a lot about x itself. Okay, and that's something we're going to study later on. So, what did I want to say about linear transformations? Let's start with the following lemma. The following are equivalent. Okay, so A, T is uniformly continuous. Okay, so uniformly continuous is that the epsilon and delta in the definition of continuity are independent of where you are in the space. B, T is continuous. t is continuous at 0. Okay, so clearly being uniformly continuous implies continuity, and clearly continuity implies continuous at 0. So the point is that being continuous at 0 is equivalent to uniformly continuity because of the linear structure, okay? And that's part of the proof that we're going to do. Okay, D is there exists a k bigger than 0 or bigger or equal than 0 such that t of x is less than k, less or equal than k, for every x in B1. Okay, so this is the unit ball in X. And E, there exists a k bigger equal than 0 such that t of x is less or equal than k times the modulus of x, times the norm of x, for every x in X. Okay, so I should make a bit of a comment. Here, this is the norm in X, and here, this is the norm in Y. Okay, in general, one doesn't denote this except if it's confusing. Sorry, this is the norm in Y, and this is the norm in X. So if it's not confusing, you clearly understand where these norms are being taken, because you're always thinking of t going from X to Y. Okay, so t of x belongs to Y, so this is the norm in Y, and x is coming from X. So you have this thing here. Okay, and before we give the proof, whenever, never, either, so this would be a definition, whenever either of these conditions hold, we say that t is a bounded or continuous linear operator. So the notation of bounded is a bit confusing, but it has to do with the fact that you're bounded in the unit ball. So being bounded in the unit ball is equivalent to continuity, so you talk about boundedness in this sense. T is a bounded or continuous linear operator, and we denote them, and we denote T belongs to the bounded linear operators, and let's try to make this a particular B, from X to Y. Okay, so maybe I'll put something like this. So B from X to Y is given by this. Okay, so let's prove the theorem. So proof A implies B implies C is quite trivial. Okay, this is followed just by the definitions. Okay, now let's see that C implies D. Okay, so what does it mean that T is continuous at 0? So if T is continuous at 0, then for any epsilon positive, there exists a delta of epsilon positive such that T of x in norm is less than epsilon for every x in the ball of radius delta epsilon. Okay, so now we have a boundedness condition in the ball of radius delta over epsilon. So if we do drawing, so here we have the ball of radius 1, and now we have a boundedness in some little ball. Okay, so before I do this drawing, I would say pick epsilon equals to 1 and take delta 1 from the definition of continuity. From the definition of continuity. Okay, so doing this, we would have that t of x is less than 1 for every x in the ball of radius delta 1. But now we can use the linearity to pass this information from the ball of radius delta 1 to the ball of radius 1. Okay, so if x is in B1, then delta 1 times x is in B delta 1. Okay, therefore t of delta 1 times x is less than 1. So in particular, using the linearity, okay, so by linearity, we have that t of x in norm is less than 1 over delta 1. And this is for every x in B1. Okay, now what happens with D implies E? So D implies E. So here we are going to have that we have boundedness in the unit ball, implies that we have that there exists a constant such that t of x is less or equal than k of k times x. So D implies E. We take x in x, and we can consider x over 2 times the norm of x is going to be in B1. Then t of x over 2 times the norm of x in norm is less than k, because, and this here is by item D. Okay, so then by linearity, we have that Tx is less or equal than 2 times Kx. And again, this is the norm in y, and this is the norm in x. Okay, so now we have done all the implications. A implies B, implies C, implies D, implies E, and now we want to show that E implies A. Okay, so having this boundedness implies that T is uniformly continuous. Okay, so again, the main point is just to use the linearity. So E implies A. Okay, so what do we want to do? We want to estimate the norm of T of x minus T of y. Okay, so we want to say that if x minus y, so for every epsilon, so okay, so if we want uniform continuity, what do we need? We need that for every epsilon positive, there exists delta epsilon positive such that for every x minus y less than epsilon, less than delta, t of x minus t of y is less than epsilon. Okay, but now here if we look at t of x minus t of y, this is the same as the norm of t of x minus y. This is by linearity. Okay, and take this up here. T of x minus y is less or equal than a k times x minus y, and this is by e. Okay, so now we can say that this here is less or equal than delta epsilon, k times delta epsilon. So we need to pick delta epsilon equal to k epsilon over k. Okay, so if we put like this is less than epsilon. Okay, and this gives us the uniform continuity of this thing. Okay, so what we've seen is that all of these conditions are equivalent. So sometimes one of these conditions is easier to check than the other ones. Okay, so that's sort of one of the points of this thing. And let's see a couple of examples of these guys. So one of the things, maybe I'll start trying to do some more examples on this kind of things. Is let's consider transformations t that are going to go from C0, 0, 1 onto R. Okay, so this is what I was saying when we take y equal to R, and this is the set. Okay, so the t which are going from B are going to be going from x to y are going to usually be denoted by x star, and this is the dual of x. Okay, so in particular when you're taking functionals that are going from C0 to R, we're considering the dual of C0, and the point is that the dual of C0 are measures. Okay, so usually they're called radon measures. Maybe later in the course we'll see the proof of that. But one of the most common measures is taking delta. So the delta is in C0, delta at 0, let's see. Okay, this delta has nothing to do with the delta of before. This is a measure. This is in C0 of 0, 1 dual, okay, which is equal to the measures in 0, 1. Okay, so what is this function? Delta of f is going to be f of 0. Okay, but this is clearly bounded, because if we take delta of f, so here we need to take the norm in R. So this delta of f is equal to the norm in R. This is f of 0, and we are taking the norm in R, so this is just the absolute value. And this guy here is clearly less or equal than f in L infinity. Okay, so the delta is a continuous, delta at 0 is a continuous linear functional on C0. Okay, so this is an example of functional. This is one of the typical examples. So what other examples can we take? So say 2. Let's consider we consider little L2, which is equal to the sequences xi, I equals to 1 up to infinity, such that the sum of xi squared is less than infinity. Okay, so this little L2 is the same as we saw a couple of classes ago as L2. So let's consider the functional t that is going from little L2 to little L2 by defining t of x is equal to the sequence ci xi I equals to 1 up to infinity. So checking that t is bounded also will give us that t is well defined, because the question is, why is this in L2? Okay, so this would be a question. So you have to give conditions on the coefficient ci for this to actually be in L2. So in this case, we would think that ci needs to be in little l infinity. So ci is in little l infinity. So what does it mean? That the supremum over I of ci in modulus is less than infinity. Okay, because I mean, if we look at the norm of t of x in little L2, this is going to be the sum from I equals to 1 up to infinity of ci xi squared. But at the same time, using the bound on the ci, this is going to be less or equal than ci. Okay, so all of this to the 1/2. This is going to be less or equal than ci in little l infinity times x in L2. Okay, and this is a sharp bound. Okay, so this guy is a sharp bound. Basically, if you want to see that this is a sharp bound, try to find something that gets a ci that gets close to the supremum, and then take x to be ei star, where I star is the one of the ci's that are getting close to the supremum. So you can actually see that this is a sharp bound, and this is the bound, the best bound that you can get. So what other is an example that people use a lot in this in this type of things is convolutions. Okay, let's see if I find my notes on this. So, okay. So another example would be convolutions. There is a bit of an easy type of convolutions, and I mean easy things of convolutions, and some that are a bit harder. So let's consider t that is going from LP to LQ. Is that what I want to do? Anyways, we'll see. So we're going to consider t of f at x, which is going to be the integral, and let's do this over r, so this is not so complicated. So this is the integral over r of kernel, so we are going to define the kernel kx minus y, f of y, d of y. Okay, so if I want to send LP to LQ, so what do I need for k? Okay, so what restriction do I need on k for this to be bounded operator. What is the idea? The idea would be that this is called Young's convolution inequality. And what we would have is that T of f in LR is less or equal than K I want Q here, so this would be Q, K in LR times F in LP. Okay, so the boundedness of this operator is if K is in LR, where where 1 over P plus 1 over R is equal to 1 over Q plus 1. Okay, so this is the condition in Young's convolution. To be able to have this bound, we need the relationship of Q, R, and P, which is given by this condition here. Okay, so not sure if I give you the proof of this, but let's try to sketch out the proof of how you prove something like this. So Young's convolution inequality, Young's convolution inequality follows from duality and Hölder's inequality. So how do we need duality? So let's say that we need, what do we need from duality? So let's see what duality means. So duality, let's say T of f is in LQ if and only if the supremum of H in LQ prime, so let's pull it, the norm of H in LQ prime of the supremum of the integral of T of f times H, this is of x, this is of x, is bounded. Okay, in fact, this supremum here is equal to the norm of T of f in LQ. Okay, so morally you can define T of f in LQ by looking at LQ prime, which is its dual, and taking the supremum over all the functions in the unit ball. Okay, and in this case we have that 1 over Q plus 1 over Q prime has to be equal to 1. So in particular, 1 over Q is equal to 1 minus 1 over Q prime. Okay, then next we can use the Hölder's inequality, but Hölder's inequality for 3 functions. So what are we going to do? We are going to take the integral of Tf x hx in R dx. This is equal to the integral over R of the integral over R of k x minus y times f of x, times f of y times h of x dx dy. And what we're going to show is that this is less or equal than k in L, this is less or equal than K in LR, F in LP, and H in LQ prime. Okay, so in particular, if this is less or equal than 1, this guy is less or equal than K in LR times F in LP. Okay, so this actually shows Young's convolution inequality. So here, to be able to show this, we need to note that because we are using the Q prime, we have this condition here. In particular, replacing this condition here, we have the 1 over P plus 1 over R plus 1 over Q prime is equal to 2. So here is a bit of algebra, but you can show is that, let me get the notes so I don't get this guy wrong. Okay, so this is a bit of a cumbersome thing, but this is something you just need to check once and then it works. So basically you can rewrite all of this. You can rewrite this integral as k x minus y to the q times f of x to the p to the 1 minus, this would be r, this would be p to the 1 minus q, then you would put f of x to the p times h of y to the q to the 1 minus 1 over r times k of x minus y to the r times h of y to the q to the 1 minus 1 over p. Okay, so what is the idea here? So the idea here is dx dy. So if you sum, if you look for k, so k is r of 1 minus q plus r times r 1 minus 1 over p, and what you can check is that r times 2 minus 1 over q minus 1 over p is equal to 1. Okay, and you can do this for the other exponents as well, and here you can just do Hölder's inequality with 1 minus 1 over q, 1 minus 1 over r, 1 minus 1 over p, which they all sum up to 1 because of this condition here. Okay, and this should be q prime, q prime, and q prime. Okay, so 1 over p plus 1 over r plus 1 over q prime is equal to 2. You sum all of these together, you get 3 minus 2, you get 1. So you can actually do Hölder's to obtain this thing here. Okay, so that was a bit of a thing. So, but usually convolutions are a good idea to have in mind, and this type of proofs are good to have like continuity from some space, from some LP space into another LP space. So one of the things that convolutions have, convolutions regularize. Convolutions regularize. Okay, so which is usually bounded. Okay, so if you make a function more regular, it's usually going to be bounded. The problem is when you differentiate. Differentiation, differentiation is usually not bounded. And this is a typical case of a linear functional which is not bounded. So we can consider t of f, so t of f that is sent to f prime in some sense, okay? So we could consider, for instance, if we consider t that is going from C0, so if we take a function f in C0 and we take t of f to be equal to f prime of 0, this is not even well defined. Okay, so we have to be a little careful. So a way perhaps to get around this, like the book actually gets around this, is let's consider the polynomials contained in C0 of 0, 1. And now we consider t of, let's say, p, which is equal to p prime. Okay, so t is linear and well defined. Okay, this is of course because I'm doing it for polynomials. As I was doing it for, if I do it for continuous functions, this is not actually well defined. But if you do it for polynomials, you can always take the differential of the polynomial, and this still is a polynomial. So, but what is the problem? Okay, so if we take Pn, which is xn, then the norm of Pn in L infinity is equal to 1. Okay, so this is in 0, 1. But if we take t of Pn, this is going to be n of x to the n minus 1. So if we take the norm in L infinity, this is equal to 1. Hence, t is not bounded. Okay, so usually if you are going to use a differentiation operator and you want it to be bounded, or if you want it to be continuous, you need to start taking a lower and lower you need to be taking a lower a space with less regularity. Okay, so if you are taking a differential of C0, you're going to be having C minus 1, C minus 2, C minus 3. If you go from C1, you're going to be going to C0 and stuff like this. Okay, so one thing that I've been trying to stress throughout this class is that all of these things of boundedness and these kind of things, they're not quite an issue. Their boundedness is not an issue for finite dimensional spaces. So this is not an issue for finite dimensional spaces. So let's write a theorem. We have t from x, y linear, such that dimension of x is finite, then t is bounded. Okay, so if we have the dimension of the domain which is finite, then t is bounded. Okay, so we don't actually need to check anything in this case. So, and a remark would be that if y is finite dimensional, we cannot say much. Not say anything about boundedness. So it has to be the domain, which is finite dimensional, and not the range. So the range y can be finite dimensional, can be r, like the case that we were looking at before, but that actually doesn't imply anything. Okay, so how do we prove this? The proof of this is fairly simple. So how do we prove this? So we consider k to be equal at the max over n of t of en. So actually, no, let's try to do this a bit better. So let's define k to be the sum from I equals to 1 up to n of t of ei norm squared to the 1/2. Okay, and we're going to do similar to the proof that we did of all the norms being equivalent. So what happens if we take the norm? So let's take x in x, then we have that x is equal to the sum from I equals to 1 up to n of lambda I ei. And the norm of x, let's call it a star, is equivalent to the norm of x2, which is equal to the sum of lambda I squared. Okay, so to the 1/2. So this is what we have done before. So now let's take this is equal. So let's take the norm of t of lambda I, t of x, and this is in the norm of y. This is going to be equal to the sum from I equals to 1 up to n of lambda I t of ei. This is by linearity. Okay, again, this is norm in y. But now this is, by using the properties of the norm, this is less or equal than the sum of lambda I times the norm of t ei. But now using Cauchy-Schwarz, this is here is by triangle inequality, and this by Cauchy-Schwarz. This is the sum of lambda I squared to the 1/2 times the sum of t of ei squared norm to the 1/2, which is less or equal than k times the norm of x2, which is less or equal than k over the little m of x star. Okay, and this is because all of the norms are equivalent in finite dimensional spaces. Okay, this actually shows that the t of x in y is less or equal than this k over m of the norm that we had originally in x. Okay, so this shows boundedness of these guys. Okay, so what's the couple of things I wanted to finish for linear spaces, linear bounded operators. Okay, so a couple of just observations. So observations. So the kernel of T is a closed subspace of X, okay? And so if T is continuous, and the proof is that if we have a continuous set and you take T inverse of a closed set, this is closed. Okay, so it's closed and it's linear space because you're taking a linear operator t. What's the other one? And this is something that maybe now seems a little weird, but then we'll see that this is a fairly important property. So t going from x to y linear and continuous, then let's call it g of t, which is equal to the x comma tx, such that x is in x, which is contained in the product x cross y, is closed in x cross y. Okay, I'm not going to prove this now, but I mean, the idea is that this just follows from the continuity of t. So if we take x, so okay, maybe let's sketch this proof a bit. So we have xn, yn in g t, and let's assume that x n converges to x and yn converges to y, then by continuity t of xn converges to y, which is equal to t of x. Okay, so if you have these guys that are converging to something, then you can actually get this thing. So the point, and this is not going to do here, so this is the proof basically. So the point that I'm not going to do here is that this theorem is an if and only if. Okay, it is an if and only if. Okay, and this is fairly strong because instead of checking the continuity of t, you can just check the closeness of the graph. So one of the things that you can assume is that t of xn is actually converging to something. And then the fact that this is converging to something, that's already giving you some information. Okay, so you can use that extra information to try to prove that in particular cases t is continuous. Okay, and then finally something I'm not going to prove, but just it follows just by triangle inequality and these kind of things, is that the space of bounded linear functions, so we take b of xy, the space, so b of xy is a linear space. Okay, so whenever we take s comma t in b of xy, so okay, so these are continuous linear functionals from the space x to y, then alpha t plus beta s is in b of x comma y for every alpha comma beta in R and st in xy. Okay, so this guy is forms a vector space, and what we're going to do in the next couple of classes is look at the linear structure and look at what structure we can inherit from the structures that we're putting in x and y. Okay, so knowing something about the b of x r is going to tell us some information over x and vice versa. Okay, thanks.